This is Lecture 1, Part 4. Earlier in this lecture, I stated that the measurement of potential only has meaning in a comparative sense. Namely, I can only ask questions like, what is the potential here, one position, versus that of another position. I'm going to restrict my discussion now to DC systems, namely direct current, so no alternating direction between the potentials. The measurement of the electromotive force or voltage of a specific source involves the creation of a circuit, in which case the meter, which has a very large internal resistance, is inserted into a circuit with the device. No current flows because the meter's resistance is huge and it essentially blocks the passage of current. So what you're measuring is the pressure, it can be thought of as a pressure, of the charges against the large resistor. I can, however, measure the voltage of a circuit in which current is flowing, but it involves measuring the voltage difference across the device. So in this particular case, I have current running through the resistor. The resistor is causing a voltage drop, in other words, a non-short circuit, you can think of it in terms of that. So I'm essentially measuring the voltage between the top horizontal conductor and the bottom horizontal conductor. The meter is in effect inserted in parallel to the actual current direction. So no current runs through the meter still, but it does act on the circuit. We'll talk about this in a little more detail. If I have two elements in the circuit, namely two resistors in this particular example, R1 and R2, I know that when the current passes through the circuit, some of the energy is dissipated by resistor number 1, altering the potential at the upper right-hand corner of the circuit as it's drawn. So the total voltage, namely the potential phi plus minus phi minus, is not the same at the upper right-hand corner. So there's loss of energy, there's a modification of the voltage. So I can independently measure the voltage drops across R1 and R2. In the example given in the illustration, I am measuring the voltage drop across R2. So the energy lost by R1 is not taken into consideration. And at the bottom of the slide on the right, I give the total relationship between the two voltage drops. I can use Ohm's law to determine these voltage drops. So the source voltage I'm going to designate as V sub S, and that's the difference in potential between phi minus and phi plus and phi minus. From that I can determine the current, the total current going through the circuit, namely I. So that would be voltage, the source voltage divided by the two resistances because they're combined in series. We'll get into this in lecture 2. The voltage drop, therefore, is across each resistor, as indicated, as the total current multiplied by the individual resistance values. If I were to measure current, I use a different type of device, namely a current meter. They're actually very similar, voltage meters and current meters. What differs is the arrangement of an internal resistor. So the current meter has a very small internal resistance. The current flowing through the meter, a wire, generates a magnetic field, and the strength of the magnetic field is translated into a current. If you were to take a current meter and put it in direct contact with a voltage source, as you did with the voltage meter, you would have a disaster. So because the internal resistance of a current meter is very small, you would be getting to the catastrophic failure of a short circuit in this case. So this, what I've drawn here, or illustrated here, should never be done in the case of connecting directly to a voltage source. If you want to measure the current flowing through a circuit, as indicated on the left, you insert the meter in series with the devices. So I would make this connection. And in this way, the small internal resistance of the meter contributes negligibly to the circuit resistance, the total circuit resistance. And this would enable me to determine the circuit current, the total current going through the circuit. So if I wanted to measure the voltage and the current simultaneously, I would put the amp meter, the current meter, into the circuit itself, and then I would apply point to point the voltage meter. I go back to the circuit that I had in the previous part, namely the floating circuit involving resistors and the battery pack. I can now demonstrate with where I would put the meters in a real as opposed to a cartoon. So the current meter would go in series with the circuit for direct measurement. The voltmeter would go point to point. So if I wanted to measure the voltage across those crazy looking two resistors in the middle, I would put the voltmeter across the terminals or the junctions between the conductor and those resistors. And that concludes part 4 and the entirety of lecture 1. Again, the usual bibliographic references.